The purpose of tonight's video is to talk about simple harmonic motion. Simple harmonic motion is when you have anything moving back and forth, so maybe like a spring oscillating back and forth, a pendulum swinging back and forth, a kid on a swing, anything that makes relatively small movements back and forth, small angles. In fact, there's definitions of the angles you can have to do simple harmonic motion. We'll get into that possibly later. But simple harmonic motion is when you have something doing small movements or simple movements back and forth. It just oscillates back and forth. And it's called simple harmonic motion because there are a lot of things that happen if you have really big swings or certain types of objects. And so we're going to ignore a lot of things as we talk about objects swinging back and forth. Like when we first started kinematics, we ignored friction. So we're going to do simple harmonic motion where we just pretend everything is making very small, very simple movements back and forth. And that's what this phrase means. Harmonic means similar motions back and forth, so it's consistent. One swing of the pendulum is similar to others, and that movement is happening there. Very simple, constant movement back and forth. Simple harmonic motion. Your pre-reading question asks you what can determine the period of a spring that's oscillating. Just so we're clear, the period of something is the time for it takes to leave one place, go to another place, and come back. So the period of this mass, if I released it from here, would be the time it took for it to go up here and come back. Similarly with a pendulum, the period would be the time it takes for it to swing over and come back to its highest point again. So swing from one high to one high, or here with the mass to go high and back to low. Anyway, one complete cycle, basically, of motion is a period. The time it takes to complete that cycle is a period. And there is an equation that tells us what exactly it is that determines the period for both a pendulum and a spring. So for a spring, which was in your pre-reading question, the things that determine its period are the spring constant of the spring, so k just like in 1/2 kx squared, and in F equals k delta x. K is the spring constant, or how stiff the spring is, so spring constant. The stiffer the spring, the smaller the period, since that k is on the bottom of the fraction, and the mass of the thing on the spring. So the bigger the mass, the longer the period. And you could actually see that happening with inertia. The more mass you have, the harder it is to get the spring to pull you back the other way. Those two things determine the period of the spring. And that period is given by this equation. The period, the time, equals 2 pi times the square root of the mass over the spring constant. You need to know that. Have that equation written down somewhere. You'll need to use it tomorrow in class. For a pendulum, the only thing that determines the period of the pendulum is the length of the pendulum string. So if we call this distance here L, it's a terrible L, that length is the only thing that affects how long it takes the pendulum to swing. So this looks like a 1 for some reason on the screen, but L. And gravity. So if we're on another planet, the period for the pendulum, the time it takes to complete one cycle, would change, but on Earth it's just the length is the only thing it depends on. And the equation that tells us the period for a swinging pendulum is 2 pi square root of L over G. You should know both of those. Know one's for a pendulum swinging and one's for a spring going back and forth. If you need to pause to write those down, you should do so now. To start our discussion on simple harmonic motion, we're going to look at the energies for pendulums and for a mass attached to a spring. And these two things are analogous. So the rules that apply to a pendulum apply to a mass oscillating or moving back and forth on a spring. So energy transformations occur the whole time. When we've got a pendulum at its highest point, it has all potential energy. And when we have a spring that's compressed however far we're going to squish it, it has all potential energy. Once that pendulum's at its lowest point, all of that potential has been converted to kinetic. Once the spring is back to its equilibrium length, all of the spring potential it had from being compressed, and by the way, remember, potential energy from a spring, 1/2 kx squared, where x is the displacement, how far it's stretched or compressed. So then it's all kinetic. It's all now moving that way. When the pendulum is back at the highest point on the other side, it's all potential. When the mass on the spring is extended as far as it's going to extend, so all of that energy has once again become spring potential. Then we swing back, all kinetic, and back up to our highest point, potential, potential. So energy transformations are happening the whole time when we've got objects oscillating in simple harmonic motion. We can also talk about these objects' velocity. Whenever the pendulum has all potential energy, it should be obvious to you that if all of its energy is potential, none is kinetic, and it has no velocity. So it has zero velocity at its highest point. Similarly, when the block is compressed all the way, it has zero velocity. When the pendulum swings to its lowest point, all of its energy has become kinetic, and so it has its maximum velocity. And same with the block. It is at the equilibrium point. All of that spring potential has turned into kinetic energy, and it keeps going. Now, if you're asking why is it all kinetic there, because you only get spring potential when you have it displaced from equilibrium. Once it's back at equilibrium, no more potential, all kinetic. The pendulum reaches its highest point. We're back at v equals 0, and the spring is now stretched out as far as it's going to go. It also has v equals 0. The block has to turn around. So another way to think about this is we've got a positive velocity happening this way, and then once the block is turning around, we've got a negative velocity, and so you have to cross through 0 velocity to change from positive to negative. So those points of maximum displacement are where it's crossing from positive velocity to negative velocity. And in fact, now that this pendulum bob starts to swing back in the other direction, once it starts moving back, its velocity will be negative. And so on its return trip, we actually call that velocity the minimum velocity, because it's the negative version of the maximum, and a negative is smaller than 0. So that's where we have our smallest velocity when it's making that return trip and it's at its lowest point. Smallest because negative is smaller than 0. Similar for our mass. It's returning, so now it has negative velocity. It's already passed through 0. Negative is smaller than 0, so this is its smallest velocity. And then back at the high point, we're at 0. And again, you could think of this as the place where we're crossing from negative over to positive. And similarly here, maybe right here, crossing from positive to negative. And we've got to pass through 0 to do both of those. So that's what their velocities look like. We can also discuss their positions, and we'll always discuss their positions from equilibrium. So I'm drawing this red line at equilibrium. Right here, if we have a standard coordinate system, we've got positive to the right, negative to the left. So right here is its smallest position, because negative is below 0. So that's its minimum displacement. It's negative displaced over here. Similarly for the block, displaced to the left, negative displacement, so that's the smallest. Then when we're at equilibrium, we obviously have 0 displacement from equilibrium. We've moved over into the positive at the furthest we're going to go, maximum displacement. Back to equilibrium, 0 displacement. And back to our starting point, which on this case is to the left, so it's negative. And that would be our minimum displacement, because negative is smaller than 0. For the spring, we can talk about forces. It's a little harder to talk about the forces on the pendulum because we always have gravity pulling straight down. But we could talk about, well, what component of gravity maybe is pulling the thing this way, what's our centripetal force since this looks like it's swinging in a circle. But that's a little more complex. Easier to just talk about the spring for now. Whenever the spring is squished the most, it has maximum force. The force is now wanting to push the spring this way. When it's at 0 at equilibrium, the spring has no force, because the equation for spring force, K times delta x, there's no displacement, so no force. When we're stretched out here, the force is now wanting to pull the spring back to the left, and so a leftward force would be a negative force, making this our smallest force, because negative is smaller than 0. Once we're back at equilibrium, no force, and then back at our squished point where the force is pushing to the right. So we have our highest force. And we can talk about acceleration. Again, at the moment, easier to talk about for the block than the pendulum. Here, if we had maximum force, that means we have maximum acceleration. These are going to be parallel. No force, no acceleration. But we would still have a velocity there. Our velocity is 0 here, where we have highest accelerations, and we're passing from positive to negative. Down here, when we're at our stretched furthest, the force is pushing it back, negative force, negative acceleration, and that's our smallest because, caught the theme, negative is smaller than 0. Back at equilibrium, no force because no displacement from equilibrium, no force, no acceleration. And again, maximum force, positive, maximum acceleration. Simple harmonic motion is represented usually by a sinusoid, so a sine curve or a cosine curve. The way you could think about this, and this is kind of a neat analogy, I think, if we put a mass on a spring and let it swing up and down, and painted it on the back with some ink that could then rub off on paper. We then scrolled the paper this way, so the paper is moving the way I've drawn the arrow, as the block moves up and down. The ink on that block as it moves up and down, and we have the paper moving behind it, would paint this sine curve that you see behind it. So we have the curve behind it made by the block swinging up and down and the paper moving off to the left. And because that block would make that sine curve, we can actually discuss where the block is using the sine curve. And we'll talk about that in terms of the amplitude, which in this case would be its maximum swing from displacement. So this is maximum displacement, delta x max, and this is its minimum displacement, delta x min. Amplitude is the maximum distance from equilibrium. And if you haven't had that before from maybe CP physics, your amplitude is always your maximum displacement from equilibrium. The furthest you go from the equilibrium is the amplitude. And we can represent, big point of this, simple harmonic motion with a sine or cosine curve. And so this graph right here represents the position of a pendulum bob or mass on a spring as a function of time, and we've measured the time in fractions of the period. So that bob starts maybe at equilibrium. That's where we started measuring. We let it swing, goes to its highest point, comes back to equilibrium, goes back to its highest point, but now on the other side, so negative, swings, and we could draw this. So we started out equilibrium, we let it swing into the positive, comes back to equilibrium. Here we let it swing, let it swing into the negative, back at equilibrium, let it swing to the positive, equilibrium, let it swing into the negative. And so this sign represents that motion, going from equilibrium into the positive, negative, and so forth. Notice again that its period t is the time it takes to make one complete cycle. So equilibrium headed up to equilibrium headed up is one full period t. So one complete cycle takes the time t, its period, which earlier in the video I showed you the equation for finding the period t, how long it takes for it to make one complete cycle. Now what might be surprising to you is the graph not only of displacement, the one I've been showing you, but then of velocity and of acceleration. So if we took the slope of this displacement curve at every point, we'd get out this velocity curve. And so notice at the place where there's maximum displacement, there's minimum velocity. So whenever your pendulum has swung out to its highest point, its velocity is 0. You should remember that from kinematics. Your highest point would always have 0 y velocity, because then you started to fall, you had to pass through 0 to go from positive to negative. And at our point of no velocity, notice here we have our lowest negative acceleration. Let's pick a couple other places to look at this. We've got an equilibrium point on displacement, highest velocity, no acceleration. So at equilibrium, our acceleration briefly passes through zero, and you can think of that as the mass on the spring, because if this were mass on a spring, no displacement, no force. This is a really helpful chart for remembering the relationship between displacement, velocity, and acceleration. In fact, it would be worth flipping your paper over that you're taking notes on, really carefully drawing these three graphs, including the fractions of the periods, and using dotted lines to line up different parts of your graph. We're going to go through this tomorrow, and if you could have this picture drawn to maybe annotate as we do discussion questions, that'd be great. In fact, I'm going to have one more slide that's just a clean version of this that I haven't drawn on, and you do want to make sure you line this up when you draw it. So if there's a high point here, and an equilibrium here, and a low point here, all those three need to be lined up perfectly. So you should make dotted lines to help you line it up, make sure they're the same size, and then you have this picture to annotate. I really thought it was in our textbook, but just flipping through, I sadly did not see this chart in here, which is really surprising because I thought I remembered it being in here when I looked at this book over the summer. But anyway, you'll need this chart. Next slide, it's coming up a clean copy. Alright, here's your clean copy. Pause. Get it copied down. Apologies that it's not in your textbook, but you want to have this to look at. It'll help you a lot tomorrow in kind of visualizing how simple harmonic motion works.